Okay, so good? Yep, all right, we're rolling. Okay. In the society that we live in, we rely so much on portable power. We can't live without it. I mean, your phones have batteries in them, your calculators have batteries in them, people with pacemakers have batteries in them. Without them, they'd die. Even the camcorder recording this video has a battery on it. And batteries, most people don't know how they work. They just sort of take for granted that they'll open up a packet, pull out a battery, plug it in, and it's just going to work. They have no idea what it is, how it works, why it works. It's just a little magic box of goodness. However, it's a lot more than that. It's about electrochemistry. It's about oxidation and reduction. Here's how it works. On reference table J, that's J as in Jumpin' Jehoshaphat, the very first battery that was ever made involved using zinc, copper nitrate, and being a single replacement reaction, the zinc took the copper's place, and the copper went off by itself in traditional fine fashion. Now, if you take a look at the positioning of these two elements, zinc and copper on reference table J, which one's higher? Absolutely. Zinc is the higher metal, and copper is listed third from the bottom. Now, what that means is simply this. The zinc 0 goes to zinc plus 2 plus 2 electrons. So in other words, the zinc is undergoing what? Oxidation. Exactly. The zinc is being oxidized. And the copper, let's put that down here, Cu plus 2, that's what it starts out as, ends up as 0, picks up 2 electrons and forms copper 0. So the copper is being reduced. Okay. We can actually build a battery on this because you can see the zinc is losing electrons, the copper's gaining the electrons. If we can somehow funnel those electrons into some electronic device that generically is called a load, before those electrons move on to the copper, then we can build ourselves a battery, taking the electrons zinc loses, passing them through an electrical device to power it, and then passing them on to the copper so the copper can be reduced. Then we'll have ourselves a battery. So we need a couple of things. We need zinc and we need copper 2 nitrate. So here's zinc, and here's some copper 2 nitrate here. Let me get my goggles on for this. Copper 2 nitrate. Lovely blue color, because after all, copper's a what? Yeah, you got that right. Okay. So, what I could do is take this piece of zinc 0 and put it into this copper 2 nitrate. However, we have a slight problem. I'm going to let this video explain what that problem is. So, if we put the zinc directly into the copper 2 sulfate, we're going to end up with a positive voltage, in fact, positive 1.10 volts. That's what I hope to be able to generate out of this battery. The problem is,
when a zinc rod is immersed in dilute acid solution, hydrogen gas is evolved and zinc ions form in the solution. The solvated hydrogen ion is represented as the hydronium ion H3O+.
Do you see that?
In this reaction, zinc is oxidized and hydrogen ion is reduced.
Whoop, and there it goes again. Now this is the reaction we're dealing with here.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation-reduction reaction occurs.
Keep an eye on the electrons.
In this reaction, zinc is again oxidized.
There's the copper
now,
ion.
However, copper 2+ ion is reduced to copper metal. In the two examples we have seen, zinc...
Did you see what happened? Where'd the electrons go? directly into the copper, do you think there's any way we could trap those electrons? There's not enough room. We can't stick a wire into that. So putting the zinc directly in the copper nitrate is not going to work. We're not going to actually be able to generate electrical current out of it. What we need to be able to do is design a way to trap the electrons as they go from the zinc to the copper. Lights again, please. And what that means simply is this. We're going to have to put them into different containers. Instead of putting the zinc directly into the copper 2 nitrate, we're going to have to pull the zinc out. So here is the copper 2 nitrate, and here's another beaker into which I'll put the zinc. Good. Now they're separated. You think we can make a battery? All right, well, let's test it. Here is a load. This is a voltmeter that will tell us the number of volts that we get. And I'm going to hook this up so that the zinc... What fell off? A little piece of plastic? All right, thanks. Okay, so I'll put that here. Now, you guys keep an eye on the voltmeter. Tell me if it jumps at all. Okay, so I'm going to hook it up to the zinc, and what am I going to hook this up to? There's nothing to hook it up to. If I put that piece of metal into the solution, then this metal might react with the solution. I don't want that to happen. I need to have something solid that I can plug this into. Okay. Metals conduct electricity, so I need to be able to put metal in there. However, copper sulfate or copper 2 nitrate, it's way at the bottom. There's only a couple of metals I could put in here and be guaranteed it wouldn't react with the copper 2 nitrate. What metals could I put in here and guarantee I wouldn't get a reaction? Gold and silver. Yeah, I know I won't do that. And, you know, to have a chunk of gold this big, yeah, I'm not going to do that. A chunk of silver would also be very expensive. But there is another metal I could use that won't produce any voltage at all when I put it in here that I can connect this wire up to. Absolutely. Copper will not react with itself. Because think about it, whatever the voltage is for oxidation, it's the opposite for reduction. We're going to end up with a voltage of 0. I'll get no reaction when copper is placed into a solution of copper nitrate. Now, did I get any voltage that time? No. Okay, so there's still some things missing. Well, copper nitrate is an ionic compound. And as an ionic compound, when it's dissolved in water, it conducts electricity. It's an electrolyte. I don't have a similar electrolyte on this side that can conduct electricity, so that may be my problem. All right, now, I've got zinc here. I need a solution that can act as an electrolyte, but that won't react with the zinc. What could I use for that?
Water.
Well, water by itself is not an electrolyte. Remember, water is covalently bonded, so by itself it doesn't conduct electricity. What I need is some ionic compound that I can dissolve in water. Yeah?
Salt water?
Okay, now I have some salt here. However, is there a guarantee that the zinc won't just react with the salt water? The salt, I mean, it would have reacted if I put it in here. Is there any guarantee I'm not going to get corrosion when I put, I mean, after all, what happens when you put metal in with salt water? It corrodes, so I don't want to do that because that'll give me a side reaction. Is there a specific compound I could use with the zinc that will guarantee the zinc doesn't react with it? Think back to what I did here. In the copper nitrate, I put copper because the copper was guaranteed to not react with the copper nitrate. So what could I put the zinc in with?
Zinc nitrate.
Bingo. Zinc nitrate. And I happen to have some zinc nitrate right here. What an amazing coincidence. What a lucky circumstance. So I'll very carefully measure out some zinc nitrate. I don't need that much. I just need enough to be able to conduct electricity. It's all clumpy. All right, and I'll add some water to it because that'll break up the compound into ions that can carry electrical charge. Do we have voltage now?
No.
No. Okay, so what could possibly be missing from this setup? Well, let's see what we have so far. We've put the zinc into a solution of zinc nitrate. We've put copper into the copper nitrate to give the wire something to hold on to. The metal strips are connected with wires that are connected to this load. Of course, it's not really doing anything right now. What the heck could be missing? Yes?
They're not connected.
What's not connected?
The zinc and the copper.
The zinc and the copper. They are connected through this because there's a conductor in the load.
But the solutions.
The solutions aren't connected. Was that what you were going to say? Okay. These two solutions aren't connected. We have a broken circuit here. Like when you flip off a light switch, it cuts the electrical circuit and doesn't allow any electricity through it. So in order to connect those two solutions together, we need the final piece of this electrochemical puzzle called a salt bridge. A salt bridge is usually a glass tube that's filled with some sort of salt solution. Now remember, a salt is any ionic compound at all. It's not just sodium chloride. This is a salt. But then again, so is copper 2 nitrate and so is zinc nitrate. They're all salts. What we need is a salt that will not interfere with the reaction. Now, it can share the same spectator ion because the spectator ion doesn't contribute anything to the reaction. So we could use sodium nitrate, we could use potassium nitrate, we could use calcium nitrate, we could use any nitrate compound at all. But I don't happen to have a spare nitrate compound sitting around. I do, however, have sodium chloride, which I can use for the salt bridge for the single reason it doesn't contain zinc, so it's not going to react with the copper. It doesn't contain copper, so it won't react with the zinc. So as long as the salt bridge doesn't contain either zinc or copper salts, it'll work. So sodium will work just fine. Now I've made up a solution of sodium chloride, and the salt bridge, well, a glass tube would be nice. Unfortunately, we don't actually have a salt bridge like that. So we're going to go low techie. We're going to soak this piece of paper towel in the salt water, and this will act as our salt bridge. Now keep an eye on the voltmeter as I place the salt bridge into position. You ready? Obviously I'm not. Okay, there we go. Here we go. Ready? And... ha! Anything happen?
No.
Nothing happened?
No.
The voltmeter didn't move at all?
No.
Oops! How about now?
Yeah.
Ah, okay. There was tape on the zinc electrode, and my alligator clip was on the tape, not the electrode. Okay, so we have, what if we didn't have the salt bridge? Would it still?
It's going down.
It's gone.
It's gone. Okay, so without the salt bridge, it doesn't work. Now there are two scales on that voltmeter. One goes up to 15, the other goes up to 5. On the scale that goes up to 5, how many volts do we have? 0.7 volts. Now this is supposed to, once the salt bridge is in place, give you a voltage of 1.10 volts. This is not. It's only giving us 0.7 volts. The reason for that is simply this. My salt bridge is introducing resistance into the system. The paper towel actually resists things moving through it. So as a result, it cuts the voltage down. Had I had a proper salt bridge, we'd be popping 1.1 volts. But because my salt bridge is introducing resistance, it's cutting down on the voltage. Okay, but it works, does it? Okay. Now what we're going to do is we're going to analyze what's going on here with this particular battery. You could actually power an LCD clock with only 0.7 volts. You could power a clock with this, and I have in the past. The only problem is the clock I used to use is now gone. I'm over it. Now, here's how it works. The oxidation end of the battery is called the anode. So the zinc strip is called the anode. It's the electrode that is where oxidation takes place, the anode. So I'm going to place this little label right here. This is the anode. The zinc strip is the anode. It kind of works like this, although I hesitate to tell you this because it's going to be completely backwards in the next lesson that I give you. Anode comes from an ion, and an anion is a what charged ion? Negative, right? A negative ion, anion. Anode is the negative electrode of your battery. So, the zinc strip is acting as the negative end of your battery. All batteries have positive and negative ends. Have you ever noticed that? Right? One's labeled positive, the other's labeled negative. And what happens if you plug it in backwards?
Nothing.
Nothing, right? Because there's a diode at the other end to prevent any electrons from going through in the wrong direction. So, the negative end and positive end are just there to tell you how to plug the battery in. Okay, well if the zinc strip is the negative end of our battery, then what's the positive end of our battery? The copper strip. Copper is being reduced, and we call that the cathode, which in our battery is the positive end of our battery. So this is the positive electrode, and we call it the cathode. There's the cathode, positive end of the battery. So now we know how to plug it in. If I were to plug it into this voltmeter here backwards, this voltmeter, actually the needle would go backwards because it doesn't have a diode to prevent that from happening. Okay. Now, what's taking place at the electrode? Well, oxidation. So we can call the entire thing on this side with the zinc and the zinc nitrate, we can call it the oxidation half cell. Which means we can call the other side, the copper and copper nitrate, we can call that, yeah, that's the reduction half cell right there. And this is the load. All right. Now, over time, one of these strips is going to get larger and the other strip is going to get smaller. When the one that gets smaller gets used up, what happens to the battery?
It shuts off.
Exactly. Or as we call it, it dies. And now with a rechargeable battery, you can plug it in and force the electrons to go back the way they came. Not all batteries are rechargeable. They actually have to say rechargeable. Otherwise, they could actually catch fire if you try to recharge them, so don't do that. Okay. So let's see if we can figure out which of these strips is going to get bigger and which one's going to get smaller. If we take a look at the chemical reaction, zinc is a reactant, copper is a product. Do reactants get used up or formed? They get used up. To form product. So which of these two strips is going to get smaller over time? Exactly. The zinc electrode will get smaller over time. And the reason is because the zinc 0, which is this metal strip, gives up electrons which go through the wire and through the load. What happened? Oh, gravity?
Every 5 seconds keeps on.
So what happens to the copper electrode? It gets larger, yeah. And the reason for that is that the electrons that the zinc loses are gained by the copper, and copper metal is formed as a product. Now there's only a couple of things that we have to look at. Do electrons go from anode to cathode or from cathode to anode? You lose electrons, they go through your load, and they're gained by the cathode. So the directions that the electrons flow will be from anode to cathode. Now, when you're doing your, like if you're looking at page 31, don't go with left or right when determining which one is the anode or cathode. From my perspective, the anode is on the right. Gravity is truly strong today. From my perspective, the anode is on the right side. From your perspective, the anode is on the left side. So don't go with left and right when you're determining who the anode and cathode is. Look at the positioning on reference table J. Whichever electrode is higher up on J, that's going to be your anode. Okay. Last thing we've got to deal with is the salt bridge. And for that, yes?
With the direction, it goes from the anode through the load and then to the...
Exactly. The whole point is, if I were to put the zinc directly in the copper solution, the electrons would transfer directly. So what I've done here is I've put them in different containers. And this entire setup allows the electrons to be pulled off the zinc through the load so that copper can gain them. And this is where that whole agent business comes into consideration. The reason why zinc is losing electrons is because the copper ions are pulling them off through the load. As a result, the electrons go through the load and the load gets electrical power. Does that make sense? Okay. Final bit. The salt bridge. The salt bridge serves two purposes. One, obviously, it completes the circuit. Without the salt bridge, there is no voltage. But it does more than just complete the circuit. It allows for ions to move from one side to the other. When zinc goes into solution, it gives you zinc plus 2 ions. The zinc solution gets an excess of positive charge. So the negative ions from the salt bridge go into the zinc side to cancel out that extra positive charge. So the anions, the negative ions, will come through the salt bridge towards the anode to cancel out the excess positive charge in here.
That is a little off of what you're saying, but what happens if you stick your finger in it?
My finger will get wet.
Okay.
Yeah, the concentration of these solutions is fairly low, but I don't want to stick my finger directly into a chemical. It's just not safe. You know, the zinc nitrate probably won't do anything to me. The copper 2 nitrate is mildly toxic, even in this concentration, so I don't really want to risk my finger. Okay. When the copper plus 2 gains electrons and becomes copper, it leaves the nitrate ion behind, meaning you end up with an excess of negative charge in the copper electrode. So to counteract the negative charge, the positive cations go through the salt bridge to cancel out the charge on that side. So the salt bridge serves two purposes. First, it allows you to have a complete circuit, and it allows you to maintain neutral conditions within each of the beakers. Excess negative positives come across to cancel them out. Excess positives, negatives come to cancel them out. And I've got some animations to show you that will really give you an excellent idea of what's going on here. So with that in mind, let's take a look at these animations. Can I get the lights, please? Okay.
The main components of the electrochemical cell are the electrodes, the half-cell solutions, the external circuit, and the salt bridge. The electrochemical cell in our animation consists of a zinc half-cell containing a zinc metal electrode and a 1 molar solution of zinc nitrate.
Just like we have.
The zinc metal gives up electrons which enter the external circuit and move to the copper half-cell. The external circuit may contain a voltmeter to measure the voltage of the cell,
like we have,
an ammeter to measure the current,
like we don't
and
have,
an electrical device such as a light or a clock.
or a cell phone or
The copper
calculator.
half cell acts as a cathode compartment. Copper plus 2 ions come to the electrode, pick up 2 electrons, and are reduced to copper atoms. The salt bridge is critical to the operation of the cell. It completes the electrical circuit and maintains electrical neutrality in each half cell.
Okay? So electrons will go from the zinc to the copper nitrate solution, but through the wire. Okay, now, what's happening in the zinc electrode?
Let's take a closer look at the zinc half cell.
Yes, let's.
The zinc half cell consists of a zinc metal electrode and a colorless solution of zinc nitrate. Notice that there are 2 nitrate ions for each zinc plus 2 ion in the solution.
As the formula would indicate.
As the zinc metal is oxidized, each zinc atom gives up 2 electrons to the electrode. The electrons enter the external circuit, and the colorless zinc plus 2 ion enters the solution.
That gives us an excess
The
positive
zinc
charge.
atom decreases in size as it forms the zinc plus 2 ion.
Okay? So you can see what happens is the zinc will be oxidized here, and the electrons, instead of going directly to copper ions, are pulled through the wire to the copper side. This puts an excess of positive ions into the zinc solution, and that's why the negative ions come through the salt bridge to counteract that. Okay?
The electrons released by the zinc metal flow through the external circuit to the copper half cell. The voltmeter reads positive 1.10 volts, indicating that this is a spontaneous reaction.
Well, it would.
It also indicates that the copper half cell has a greater electron attracting ability than the zinc half cell.
It would read 1.1 volts if we had a fancy, this is actually called a U-tube. They came up with the name for the U-tube long before they ever invented YouTube. You know, Y-O-U-tube. Okay. Next stage. What's happening on the copper side?
As the electrons leave the external circuit, let's take a closer look at the copper half cell. As the electrons enter the copper metal electrode, copper plus 2 ions from the solution come to the electrode. They pick up 2 electrons and are converted to copper atoms.
So these are
The copper atoms plate onto the metal electrode.
Keep an eye on
Notice
the
the
color of the
increase in
solution,
size as the copper plus 2 ion converts to a copper atom.
because it's gaining another energy level.
As the reduction reaction continues, the copper plus 2 ion solution decreases and the blue color of the solution fades.
Since the blue color is due to the transition metal copper, when the copper leaves the solution will lose its color. So when you've run out of copper ions, then you can't get any more electrons to be gained, the battery will die. The electrons that are gained are the same electrons that were lost by the zinc. Also notice we pulled positive charge out of the solution. So the salt bridge provides extra positive charge to that side to keep both solutions neutral. Here are a couple of animations regarding the salt bridge.
The salt bridge completes the circuit in the cell and bridges the anode and cathode compartments. The salt bridge contains a solution of an ionic compound such as potassium nitrate. The salt bridge maintains electrical neutrality in the 2 half cells. As the zinc metal is oxidized to zinc plus 2 ions, there is an excess of zinc ions in the anode compartment. Nitrate ions move out of the salt bridge into the anode compartment to balance the excess zinc ions. As the copper plus 2 ions are reduced to copper atoms, there is an excess of nitrate ions in the cathode compartment. Potassium plus 1 ions move out of the salt bridge into the cathode compartment to balance the excess nitrate ions. The flow of potassium ions and nitrate ions out of the salt bridge completes the circuit.
Now in our salt bridge, since we use sodium chloride, the chloride cancels out the excess zinc, and the sodium cancels out the excess nitrate. And as a result, we maintain electrical neutrality in both of our half cells. Okay. And finally,
if the salt bridge is removed from the half cell compartment, the circuit is broken. The cell voltage goes from positive 1.10 volts to 0.
Is that what happened when I removed the salt bridge? Yes. Excellent. So that's how a battery works. Essentially, zinc is being oxidized by copper ions, but by putting them into separate half cells, we can actually capture those electrons and use them to power an electrical device. No longer is the battery just a little magic box for you. All batteries work exactly the same way, except the batteries you're used to are dry cells, not wet cells like this one. Was that your question? Yeah. I mean, this would be really hard to fit in your cell phone. What they use instead is a very well-engineered design that actually, instead of using a liquid electrolyte, uses a paste as an electrolyte. And it actually does a very good job. There are some that also use a gel electrolyte. Exactly. When a battery bursts, all that goop that comes out of it is the electrolyte gel or paste that's coming out of it. There is one kind of battery that still is a wet cell, and it's the battery that's in your car. Car batteries are still wet cells. Their electrolyte is a concentrated solution of sulfuric acid, which is where the term battery acid comes from. There's no battery acid in here. There's a mildly acidic electrolyte, but not a wicked, nasty electrolyte like you'll find in a car battery. Although Mr. Landsman told me that he has a boat, and he says that there's new batteries that are out now that are lead acid batteries, but instead of the acid just like sort of floating out there, it's trapped in this sort of matrix, I guess you could say, of material in such a way that even if you cut the battery in half with a chainsaw, no battery acid can leak out. So it kind of holds it in place, and it's a lot safer to use. It's also 5 times the price because of the engineering and materials that go into that matrix material. Okay. To finish this off, we have a music video. And this one is going to involve group participation.
Oh.
By the way, this is, whoops. This is probably my most famous music video. Students actually sang it at Cabaret Night a few years back while I was there, and I'll tell you, it was an absolutely amazing experience. It will get stuck in your head. It'll make you want to tear your hair out. This is why I have no hair. It's called You Start at the Anode, and it takes you through the sequence of what's happening to negatively charged particles from the beginning all the way back to the end. But the sequence doesn't end just one time around, and neither does this song. So I'll get you started, and you guys can join in. Vital to make a battery is this electrochemistry. You take 2 half cells and connect them up so well with a load to power in between. You need to have electrodes, you see, full of that metallicity. Let electrons flow, across the salt bridge we go, allowing us to make electricity. We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Everybody now, we start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire. I'm really getting tired. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? The anode!
Okay.
Yeah! Phew!
That was interesting.
That was pathetic. Usually, some people start joining in by the last person. All right. I couldn't even get a where from you guys for crying out loud. So you know what? We're gonna do it again.
Guys, thank you.
Vital to make a battery is this electrochemistry. You take two half cells and connect them up so well, with a load to power in between. You need to have electrodes, you see, full of that metallicity. Then electrons flow across the salt bridge we go, allowing us to make electricity. 3, 2, 1, and start at the anode. Electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Everybody now! We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go and the anions go through the salt bridge back to where? Where? We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? Where? The anode. There you go. Give yourselves a hand. Now there are some mnemonics that you can use to help you to remember that the anode is where oxidation takes place and that reduction takes place at the cathode. So here are those mnemonics. Let's build them up one at a time, shall we? Anode is where oxidation takes place. Anode is where oxidation takes place. Anode is where oxidation takes place. An-ox. Alright, if you thought that was goofy, you're just going to love this next one. Reduction takes place at the cathode. Reduction takes place at the cathode. Reduction takes place at the cathode. Red cat. So that's how you can remember. Anode is where oxidation takes place. An-ox. Reduction takes place at the cathode. Red cat. And those are your two mnemonics for the electrodes. Now there is one other mnemonic that I need to share with you. The anode gets smaller, right? It gets used up because it's oxidized. But to help you remember that the anode gets smaller, an-ox is a type of, well, it's kind of related to a cow, isn't it, right? An-ox is sort of cow-ish. And over time, it gets smaller, it gets skinnier, so skinny cow. And that is electrochemistry with voltaic cells. Thank you.